Previously, we have described the components of consciousness and the function block diagram describing how they can work together as a system. We also have listed key parameters to identify consciousness. Now, we will describe how consciousness could emerge as a product of natural process and come up with strategies to achieve those key parameters. Let's recall the function block diagram for consciousness from previous video, which was built using only some basic knowledge of computation.
Information from environment is collected by input interface. It is stored in memory block depicting current state. Soon it will be transferred to memory block depicting past state, simply because time flows, and environment changes. Current state memory will be updated by new information. In information stored in past state memory block, some patterns can be found which can be used to draw causality mapping and other relationships among different things. Combined with current and past state memory, causality mapping can be used to predict future state. Predicted future can be compared to preferred state, which may come from random occurrence, at least initially. This is what we usually call goals. The discrepancy between preferred future and predicted future can be used to make action plan. Finally, the action plan is executed by making changes to the environment through output interface. The action can also be directed introspectively, such as identifying false input data as illusion or deception, correcting corrupted past memory, updating causality mapping, updating future prediction, and updating action plan. In the end, natural selection will eliminate those conscious systems whose components don't support their own survivals. Some environments may be more tolerant to deviations, while some others may be less forgiving, and they can change from time to time. Highly conscious systems are more resilient to those changes, while less conscious systems are more dependent on environmental conditions.
Some simpler systems may lack of some components, or they are not well developed yet. They are automatons that can only react to their immediate inputs. Nevertheless, some of those automatons can be better at survival than some others, which would make them more numerous in nature. The competition for finite resources effectively force them to improve their internal system to be better at survival. Simplest systems may occur naturally through some random processes. But they are much less likely for more complex systems. It's virtually impossible for a complex system like a multicellular organism to be produced by a single-shot random event. They must have emerged gradually through continuous improvement of components and parameters of previously existing conscious systems. Our previous video has listed key parameters of conscious systems. Not all of them are equally critical for the survival of simplest systems which has a chance to emerge naturally. Two parameters stand out as the most critical for them, which are robustness and flexibility. At a glance, they might seem contradictory, but at a closer look, we will see that they are naturally important. Any system that's too fragile in its environment will soon disappear. If in the future a similar system should exist, it would have to emerge independently. Environmental conditions change over time. Flexibility is needed to cope with it. Robustness or resistance to errors can be achieved by strengthening protection, which effectively reduce the impacts of environment that would otherwise change the internal system. Another way of preserving existing systems is by making backup copies. Thus, when some of the copies are inevitably destroyed, there's still a chance that some other copies survive. To be sustainable, the reproductive rate must be at least the same as the death rate. Identical backup copies are still vulnerable to common mode failures. Some variations among those copies might be helpful here. They can emerge naturally through random mutations. More complex systems might develop some forms of selective changes. Naturally emerging simple biological systems are known to have developed aforementioned methods. They developed reproductive systems, stronger cell membrane, selective genetic transfer, while still allowing some random mutations. Theodosius Dobzhansky said that nothing in biology makes sense except in the light of evolution. Once reproductive systems developed in nature, evolutionary process can start to develop more complex systems faster. It's reasonably assumed that the other components of evolution, which are variation and selection, can emerge more easily in nature. The exponential nature of reproduction would inevitably deplete available resources to sustain all occurring organisms. It forces them to compete and involve in some form of arms race. The competition leads to improvement of efficiency and optimal resource allocations. It then leads to goal alignment, which is being better at survival by improving decision-making process. The other parameters then start to show important roles in the emergence of consciousness. Improvement in update rate and data resolution of each components, also memory size and time span can help organisms to win the competition and become better at survival. The update rate is also affected by data transfer rate between components. Efficient data structure and data compression algorithm can also improve the overall performance. Now let's go back to the function block of consciousness. Note that this diagram ignores many functionalities not directly related to consciousness, but crucial for the survival of organisms, such as collecting matter and energy from the environment, reproduction mechanism, defensive and offensive mechanism. You may also note that each function block in isolation is useless for survival of the organism, which makes them unlikely to emerge independently. It seems more likely that early organisms acquired physical parts which acted roughly as several function blocks at once. The functional speciation and physical segregation may come later on. As we can learn from video compression, current state has a lot of similarities as the past and future states, hence depicting them can be achieved by the same physical part with only slight modifications. On the other hand, action plan may as well already contain preferred state and causality mapping. No matter how simple a system is, it comes with a cost that requires some resources in the form of matter and energy. It can only be justified if it can increase the chance for the survival of the system. In the input side, it can be done by sensing possible dangers or possible resources. In the output side, it can be done by moving away or towards sensed objects, or forming barrier to separate itself from the environment. At the center, it must make connections between possible states of input and possible state of output properly. A rough classification of inputs into pain, pleasure, or neither is useful to select appropriate actions as the output. There are many parameters of the environment that can be used as system input of organisms, such as light, sound, pressure, temperature, and chemical substances. Simple organisms usually only have a few sensor types which are critically relevant to their survival. No matter how simple a system is, it comes with a cost that requires some resources in the form of matter and energy. It can only be justified if it can increase the chance for the survival of the system. In the input side, it can be done by sensing possible dangers or possible resources. In the output side, it can be done by moving away or towards sensed objects, or forming barrier to separate itself from the environment. At the center, it must make connections between possible states of input and possible state of output properly. The simplest response is reflex, with almost immediate action following input sensing, without much internal processing in between. A system that only has reflex response to stimulations are not usually considered as conscious. A rough classification of inputs into pain and pleasure as proxies to threat and opportunity, respectively, is useful to select appropriate actions as the output. In the end, the ultimate results of each event is death or survival. For simple organisms, pain and pleasure can be seen as expectation of death or survival in near future. Systems with mostly correct connections from their senses of pain and pleasure to real threats and opportunities are more likely to survive. But in some cases, there will be some false or delayed connections. Sometimes, enduring some pain at present is necessary to survive from future threats. Sometimes, neglecting or avoiding immediate pleasure is necessary to get bigger opportunity in the future. This temporal factor adds complexity to be solved by the system, but it would be necessary for some organisms to survive harsher environment and competitions. To process this temporal factor, the system needs to spare its memory space to represent the past and future states. It also needs to draw causality mapping and preferred states in order to make optimal action plans. Expectations of future pain and pleasure are called fear and happiness. With increased complexity, other kinds of emotions can be expressed. They add more precision to internal state of the system by having more possible states, such as angry, sad, disgusted, excited, hungry, satiated, etc. Having increasingly more precise and accurate model of the environment can help organisms to solve problems and achieve their preferred states more effectively and efficiently. Rational thinking can then start to emerge. In the end, the ultimate result in decision-making process of organisms is whether or not they survive and thrive in the long term. It requires goal alignment to the universal terminal goal. It also needs prioritization among preferred states, since getting them all is virtually impossible. Getting the priority correctly is what we call wisdom. The emergence of components in natural conscious systems might be similar to the development of artificial neural network. It was indeed based on natural neural networks as the reference model, since that's what known biological systems which show some decent level of consciousness consist of. In early stages, there could be the smallest number of layers available, which are input and output layer. They can act roughly as all required function blocks for consciousness. Although not as effective and efficient as theoretically possible, they might just be enough when the environmental challenge is less demanding and competition is not fierce yet. As shown in the diagram, sense data are sequentially fed to input node, and the weight of connections between the nodes determine the final decisions to take. In simple or shallow artificial neural networks, the weight of the connections start with arbitrary value, and then are adjusted using training data and backpropagation algorithm. In the natural neural networks, the training and deployment may not have a clear-cut distinction. They would have to learn by doing. Instead of supervised learning which needs a supervisor to give feedback, simple pain and pleasure could be used as raw but useful feedback mechanism. It effectively uses environment to complete a closed-loop system, just like a typical process control system. Additional nodes in input layer and output layer add data resolution, although they have potential to reduce update rate. But keeping only 2 layers of neural network limits its capability to make abstraction and capture adequate complexity of the real world to make effective and efficient decisions. That's where additional layer is needed. More complex problems need more layers to solve, generally speaking. Although, adding more layers has its own challenge and difficulty, at least in the development of artificial neural network, as explained in some YouTube video linked in the description. Neural networks with many layers are commonly called deep neural networks. Environment provides a lot of information, which is too much for any finite system to process. Thus it becomes necessary for input interface to filter out non-essential input data. Significance of data might depend on situations, hence further filtering out process which is flexible to context would be necessary. Data compression is also necessary to reduce systems load by removing redundancy and removing less significant data. The data would then be encoded to the appropriate format compatible with internal mechanism. Pre-processed data would then be processed by internal mechanism, with main purpose of making best decisions. The decisions are then prepared to execute by reversing the encoding process, which is often called decoding. The result is then passed on to the output interface to have physical impact on the environment. A lot of data processing in conscious systems involve conversion from time domain or space domain to frequency domain, and vice versa, similar to what's known as Fourier transform and inverse Fourier transform, respectively. Modern multimedia devices extensively use fast Fourier transform for image, audio, and video processing. Similar mechanism might be used in natural neural networks. Our next video will try to describe extended consciousness. It's inspired by the extended phenotype by Richard Dawkins. Stay tuned.